want to ask questions? You want me to blaze on? Yes, sir. 6.5 problem 5. Okay.
Rectangular swimming pool 60 feet long, 10 feet wide, and 7 feet with water to the crest of 7 feet.
I forgot how deep you said it was. 7 feet deep.
10 feet deep.
10 feet deep. Filled to water to a depth of 7 feet.
Use an integral to find the work required to pump all the water out over the top. Take out the density of water equals 62.4 pounds per cubic foot.
Okay, we're pumping water out of a rectangular swimming pool. So we're given the dimensions, 60 feet long, 10 feet deep, 10 feet wide. Let's make this the 60. That's the 10. And it looks like I drew it to scale. That's a 10. We don't need to know all of that. We just need to think of what a slice of water looks like. Because our plan in computing work, the work integral is going to look like depth of the water. Now we got density times the volume of the slice times the distance the slice has to go. The volume of the slice depends on which face you put on your grid. I'm just going to put the 60 by 10 on my grid. And here's my X and Y axis. Put the 60-foot one here. So that it goes from -30 to 30. It's 10 feet deep. So this ordered pair here is 0, 10. And then we make a slice, a 2-dimensional slice. Oh, don't tell me I broke another pair of glasses. That bites. Where did I break them? Well, it's all blurry. Okay, so here we go. We're going to make a slice of that liquid. So that corresponds to making a cut across here of thickness delta Y, and all the way back it gives us an infinitely thin slice of that liquid. So we've got a rectangular slab whose volume we need to find. And it's just the product of the 3 dimensions. And since the edges are the same, the product of the 3 dimensions to get the volume of the slice is going to be 60 times 10 times delta Y. Agree? Then the distance, I put it at some random Y coordinate. I need to take it from here to the top. So what will you write as your distance?
10 minus 5.
10 minus y. So our definite integral will have the 62.4 right here. I'll keep the 60 times the 10 right here. Let's go ahead and multiply that as 600. We'll put the dy on the very end, and I'll put the 10 minus y here. And then the cuts of liquid occur up the y-axis from y is equal to 0 to y is equal to 10, because it's, oh, I'm sorry, not to 10. The depth is only to 7 feet. So let's put the water to here at 7. So these numbers go from 0 to 7. You okay to there? Do you need me to integrate it, or are you good with the integration? You can do it? Because these are constants, they come out, you get 10y minus y squared over 2, put in the 7, and you're done. And include the units, right? Foot pounds. You need another one? All right, let me finish up. Nope, we do have another one.
Next problem 6. Fuel oil tank with an upright cylinder. Buried so that its circular top is 14 feet below that level. It has a radius of 6 feet and it's 18 feet high. The current oil level is only 16 feet deep. The work required to pump all the oil in the surface. Oil waste will be found per feet.
There's the story. 18-foot high tank is buried 14 feet below the surface. The tank is only filled to a depth of 16 feet with oil weighing 50 pounds per cubic feet. Pump all of that oil to the surface. Let's put that on a grid. Okay, so we got that. That ordered pair right here is 0.16. If I add 14 to that, this ordered pair right here is 0.30. Oops, sorry, this is 0.18. The liquid goes to 16. And then we make a slice and pull the slice out. And what shape will a slice of liquid have?
Circular disc.
Circular disc. The slice is a disc. 18 plus 14. Yeah, I was close. 18 plus 14 is 32. It's not a good numbers day. So the slice is a circular disc. That comes into play when we find the volume. How do I find the volume of a circular disc?
Pi r squared
Pi r
delta.
squared times the thickness. Does the radius vary where I place the slice?
No.
It's going to be the same as the radius of the tank, which is 6. And then the thickness is our delta y, which becomes the dy in the integral sign. The distance, we're going to take it from where it is, it's some arbitrary y coordinate, and we need to pump it up to the height of 32 on my grid. So do you agree the distance is 32 minus y? so our integral will look like density times the volume times the distance. Density was 50 pounds per cubic feet. This multiplies to 36 pi. And then the delta y gives me the dy on the end. And then the distance we said was 32 minus y. What do we do with the numbers on the integral sign? 0 to 16, the depth of the liquid. Perfect, perfect. And then again, it's not hard to integrate. All of this stuff is a constant. It comes out when you're integrating another linear term. Okay. Good. All right, let's do the last part of section 6.5. The last part of section 6.5 is involved in finding the center of mass. So there it is, look at there. If you have a thin plate, thin, so thin that it's almost dimensionless. If you have a thin plate with some sort of irregular shape, the center of mass is the point on that plate that I can put my finger and balance that plate on my finger without it wobbling and falling off. But of course, it wants to wobble and fall off. It's being pulled in the next direction and it's being pulled in a Y direction to fall off my finger. Those tendencies of that plate from any point to wander around the Y-axis or the X-axis are called the moments with respect to the Y-axis and the X-axis. The center of mass has something to do with those moments of inertia. The center of mass is an ordered pair. So I'm going to draw this on the XY plane. Maybe we've got, I gotta sneeze. No, maybe we got some sort of irregular shaped region in here bounded by some curves. Center of mass is an ordered pair. Denoted X bar, Y bar. Typically, we use the little bar over the variables to denote an average. So that's what it's going to be. It's an average. It's a weighted average, though, because this plate has an irregular shape, and it could very possibly have different densities at each point. We're going to assume in the deriving of these formulas that the density at each point is uniform. So let's assume, ooh, there's 3 L's in wheel. Why not? We will assume that the density on this plate is uniform. That is the same at every point. Okay, so let's just denote the density at each point. as, I think they use a row in this section. A script looking key. So if the density is the same at each point, then really it's just the shape of the region that plays the biggest role, or the area of the region. The area of the region, when you multiply it with its density, is going to be called its mass. So the mass of the region is just the density times the area. Now we found area in section 6.1 by top graph minus bottom graph, integrate that from A to B. Or if we have to change the coordinates to y, we do things dy. But density times area is the mass. When we're averaging things, we're going to take the average of our moments with respect to the mass of the region to find our x bar and y bar. We're going to denote my, capital My. We're going to denote mass with a little m. So we're going to say capital My is the moment of inertia with respect to the y-axis. And m, capital M subscript x, it will be the moment with respect to the x-axis. So I didn't want to write with respect to again, so I just wrote WRT. These again are the tendencies of this plate to pull around the x-axis or the y-axis depending on the point. So it depends on the location of the point. If my finger is here, there's going to be some pull in this direction, and some pull in that direction. So if I'm holding it like this and it wants to wobble off my finger. So it varies from point to point. What we'll do is we'll make a slice of this region in the dx kind of manner. So assume we have a top graph and a bottom graph. We make a slice of the region. We're going to slice it up into an infinite number of these, and we'll try to find the center of mass in each slice, and then we'll average those out to get the center of mass all together. Average them out by an integral, right? An integral sums things up. And then when we do the average, we divide by the total mass. So here's how we're going to compute the moment of inertia with respect to each of these axes. Suppose that we have a top graph and a bottom graph, an f of x and a g of x. So let's say that this graph here is y is equal to f of x, and this bit here is y is equal to g of x. Okay, now take an arbitrary ordered pairing here, any point. The moment of inertia with respect to the y-axis is going to be the distance of that point from the y-axis times the area of that y-axis, and include the density, but since it's a constant, we can always factor it out. Well, if I move this rectangle across that region, then this distance of any rectangle from the y-axis is just some x that lies in the region. So this distance is going to be x. The area of this strip will be top graph minus bottom graph. So for that particular strip, the moment is going to be x times f of x minus g of x. Now, of course, if I'm doing it per strip, then I'd have it subscripted with my xk, where xk is an arbitrary x in the k subdivision on the x-axis. But when we set up a Riemann sum of each of those xk's, we get a definite integral from a to b, and that's the moment with respect to the y-axis. To get the moment with respect to the x-axis, we kind of do the same thing. We pick a point in here that's the center of the strip, and we measure the distance from the x-axis to the center of the strip. But that again is going to depend on where we put the strip. If it's the center of this, then it's the average of the two y values, the one on top with the one on the bottom. So this y value here would be f of x plus g of x divided by 2. That's that length right here. That's that y. So it's going to be the average for each one. So I average that distance. So instead of having an x here, I would have an average y. And then I take that average y and I multiply it with the area of the strip. And then I sum them up for each strip. I forgot the density term. Since our density is constant, I can pull it out here. If you're ever doing a problem which density is not constant, it would remain in the integral sign. So for the sake of being most general, I'll put my density right here in front of both of those. For us, it's a constant, we can factor it out. Then if you take those two moments and divide them by the mass, where the mass is just density times area, if you divide each of those by the mass, you'll have that ordered pair x bar, y bar, where x bar is this moment divided by the mass, and y bar is this moment divided by the mass. So I'm using the my to calculate x bar because my x's march across this way, away from the y-axis, and my moment with respect to the x-axis finds my y's because they march that way. So it's an easy enough formula to use. This one simplifies a little bit. If you take f plus g and multiply it with f minus g, what will you get? F squared minus g squared. So I can take this 1/2 out front and make it a cleaner looking formula. 1/2 density f of x squared minus g of x squared dx. It's easier to remember this way. Average y times the area times the density. But eventually you'll have to multiply it out through these intervals. Okay? All right, so let's take kind of an easy looking graph. Let's take the graph of y is equal to x squared plus 4. The x-axis bounds it on the bottom, and two vertical lines, say from x is equal to -2 to x is equal to 2. So consider this region bounded by those 4 equations to be our thin plate, and let's find the center of mass of region R. So assume constant density of rho. Let's get a graph of that region first. Because the picture saves us some work. Imagine that being like a thin piece of metal, and now you want to balance it on your finger. Is it obvious to you that your finger's gonna have to be somewhere on this y-axis? Probably a little taller because of these loops up here, maybe about right here, where this ordered pair is 0, 4. So we're kind of guessing our center of mass to have as our x bar 0, and as our y bar some number in the neighborhood of 3. Would that be a good educated guess? Okay, well, let's do the calculating. Okay, we need to calculate 3 integrals. First, let's find the mass. Mass is just density times the area. Area as an integral is top graph minus bottom graph. So y is equal to x squared plus 4 minus 0. From -2 to 2. And so we integrate that. Our density constant here. We have x cubed over 3 plus 4x from -2 to 2. 2 cubed is 8. So I have 8/3 plus 8. Put the -2 in there. And I have a -8/3 minus 8. That minus sign means I'm going to add them together. So I get 16/3 plus 16. Common denominator there says I have 48/3 plus 16/3. 48 plus 16 is 54/3. That close?
64.
64/3. It's not a good number, Dave. Oops, that's not equal to, that's times. And so that's mass. Hang on to it. Okay, next I'm going to compute the moment of inertia with respect to the y-axis. My top graph is the parabola. Bottom graph is the x-axis, y is equal to 0. So we just take x times x squared plus 4 and integrate it over that same range. I'm going to put it. Put it over here. Okay, so the moment with respect to the y-axis will be the integral from a to b of the density x f of x minus g of x dx. So in our example, it's the integral from -2 to 2 times our density times x squared plus 4 dx. So let's send the x through the parentheses. I can factor out the row. We're going to integrate x cubed plus 4x. We get x to the 4th over 4 plus 2x squared from -2 to 2. 2 to a power and -2 to a power will give you the same number, right? 2 to the 4th and -2 to the 4th are the same. 2 squared and -2 squared are the same. So can you see how this is going to give us 0? And that's what we said. The moment of inertia with respect to the y-axis should be 0, because our center of mass should be on the y-axis since it's symmetric there. That's not true if density varies. Okay. All right, now we're going to compute the moment of inertia with respect to the x-axis. So that's the one where we have to average things. So I've got a 1/2 here, then my density, and then I have the f of x squared minus g of x squared. So the 1/2 comes from doing the average. The f of x plus the g of x is the product of f plus x, f plus g, f minus g. But our g is 0, and our f is x squared plus 4. So the integral we compute here is 1/2, -2 to 2, the density times x squared plus 4 squared, and that's 0. We'll have to square this in order to integrate it. I'll get x to the 4th plus 8x squared plus 16. Now integrate, I'm going to take the density out there with the 1/2. I'll get x to the 5th over 5 plus 8x cubed over 3 plus 16x. So notice that all my powers are odd. So that when I put a 2 in there and a -2 in there, I get the same number, but opposite in sign. So I'm going to have 2 to the 5th is 32. 2 cubed is 8. 8 times 8 is 64. And 2 times 16 is 32. Now when I put the -2 in there, I'm going to get a -32 to the 5th. -64 over 3. And a -32. So this means I'm going to actually add those numbers to themselves. So I'm going to get 64 over 5 plus 128 over 3. Yeah. Why shouldn't I? Why don't I cancel the 2? Let's do that. Thank you for saying that. So I got 2 of those, so let's just cancel that with that one. And so I have all of that. Let's go ahead and get a, oh, do I want a common denominator?
No.
Yes, we do. We got to do it. We got to get a number. Because how would you know that it's 3-ish? So I got to get a number. Okay. So 3 times 32 is 96. 5 times 64, 320.
Mhm.
How much?
896.
Thank you. So that's mx. And so our center of mass, x bar, y bar, is the ratio of my to m and mx to m. My was 0. Mx was at 896 over 15. Then I'm going to divide that by 64 over 3. The rows will cancel. So if I flip and multiply, first I get 5 out of that. 8 goes into both of these. Four goes into both of those. Four times 8 is 32. Also 2 goes into 84. 42 times. So I get 42 over 5.
I think we did something wrong.
I did something wrong. Because it has to be bigger, huh?
Yeah.
Oh, I got, oh, no. Yeah, I did something wrong. Dang numbers, dang numbers.
1128.
14 over 5? Which is almost 3, isn't it?
Mhm. Oh, I have a question.
Oh, I was giving you a high five.
That too. Why is that defined as n sub y if like we're using that as the x coordinate for like
Because
our
it
x, y?
measures in the x direction, an x distance from the y-axis. So that's called the moment with respect to the y-axis.
Oh,
So it's
okay.
adding up the x's going this way as we partition our rectangles through there.
So it means like the distance from the y.
Right.
Okay.
Yes,
How do you make the math so fast?
I screw up my answer, is how. That's how I just make numbers up and boom, and let whatever comes out of my mouth come out. But actually, I spent many semesters teaching the elementary ed majors how to teach children how to do mental math. So I had to fake that too. Was there a hand over here somewhere?
Is this still on balance? I think I might have moved it a bit.
You moved it? It's okay. It looks okay.
Could you explain one more time, like the components of the M sub y and M sub x?
The components
Yeah. like
from the
what do-
formula,
Yeah. What do each of those represent?
put the general formula back up here. Have a rectangular strip and say an X bar K and a Y bar K to be the center of that strip. Then that X bar comes from an average distance of your X from the Y axis, that distance, times the area of that strip. So the area of the strip is going to be an F minus a G, right? And then that distance is just going to be some X coordinate depending on where I put the strip in the region. So that varies. So I said the moment with respect to the y-axis sums up those kind of things and gives us that X times the area with our density. With respect to the y-axis, I need to measure going upward. So that y value going upward there is an average of all the y values in that particular strip. So that y sub k is the average of the y values. I average the two y values that way. Then I multiply that with the area of the strip. And then add all of those up. It's when you multiply these two together that you get the f squared minus the g squared. That's why I think it's easier to remember the formula if you leave it without multiplying it out. But when you see this in your engineering books, you'll see squares and then you think, where the heck do squares come from? They come from average. Okay. But it does seem like it's backwards because to find the average of all the x's, we take that one, divide it by m. But it is that one because we're marching that rectangular strip across the region. And then y bar is the other one because there's nothing else to use. So we're going to use the other one. So the end result is a calculation that's relatively easy, but it's kind of like polynomial yucky yuck, unless I keep my problems relatively small, right? So how many times did we find the area of the region enclosed by y is equal to x squared and y is equal to x cubed? A gazillion, right? Well, let's find the center of mass of that region. Find the center of mass of the region bounded by y is equal to x squared and y is equal to x cubed, assuming a constant density. Draw that region up over here. They intersect at 0, 0, and 1, 1. Which one's on the bottom between 0, 0, and 1, 1? X cubed is. They almost have the same shape in that interval. So there's y is equal to x cubed. And then here's y is equal to x squared. So both x bar and y bar should be fractions. So the mass is density times area. Let's do the mass interval first. There's my constant density. My area is top graph minus bottom graph. So when we integrate, we have x cubed over 3 minus x to the 4th over 4. From 0 to 1, that's 1/3 minus 1/4. So a common denominator of 12 gives me 4/12 minus 3/12. And so I get 1/12 as my unit of area. Yes. I'm going to give it to you right here in your head. I'm going to give it to you on paper on the review sheet. And then if you do some breathing exercises with it in front of you, it'll absorb into your brain. And there it is. You're going to play some sort of mythical music in the background when you're doing this.
You said you were on the review sheet, right?
It'll be on the review sheet, but you're going to not,
Oh, okay.
I'm not going to let you use it on the test.
Are you telling me I've gone this whole time without understanding the fundamental idea behind learning math?
That's right. It's just breathing. It's just breathing. Math is breathing. It's just like that breathing the pregnant lady does.
Yeah, that's been me every test.
So that's why I knew you were getting it.
Yeah,
Cole's got this down. The scream at the end is everything.
yeah.
Okay, the moment with respect to the y-axis. Moment with respect to the y-axis has an x in here times an f minus g. And so I'm going from 0 to 1, x squared minus x cubed. So this time I got to integrate x cubed minus x to the 4th. And we get x to the 4th over 4 minus x to the 5th over 5 from 0 to 1. And so we have 1/4 minus 1/5. Common denominator of 20 says I have 5 20s minus 4 20s. So I get 1/20.
So if the denominator on the left is smaller than the denominator on the right, is it just 1/5 products of the denominator?
If they differ by 1. 1/6 times 1/6 minus 1/7 would be
1/42.
1/42. See, you too can teach elementary kids, or elementary teachers how to teach elementary kids. There you go. Yeah. All right, MX had that average in it. So we had a density, we had a half that came from the average, we had an F plus G times an F minus G. But F plus G times F minus G is the same as F squared minus G squared. So in this case, it might be just as easy to write that. So we'll have density times a half times the integral from 0 to 1. Top graph is x squared. Bottom graph is x cubed. And so this time we're integrating x to the 4th minus x to the 6th. And so we get x to the 5th over 5 minus x to the 7 over 7 from 0 to 1. So I have 1/5 minus 1/7. Common denominator is 35. So we have 7 over 35 minus 5 over 35. So we get 2 over 35. All right, cancel that 2 with the 1/2. And I get density times 1 over 35 is our moment with respect to the x-axis. So finally, we set up our ordered pairs. First member of the ordered pair has the moment with respect to the y-axis divided by the mass. So that number was density times 1 over 20. Mass was density times 1 over 12. Density constants cancel. Flip and multiply, and I get 12 over 20. I think I can do a 4 in each of those, so I get a 3/5 as my x. Second member of the ordered pair has the moment with respect to the x-axis divided by the mass. So I take my density times 1 over 35. Divided by my density times 1 over 12. Densities again cancel, and we get 12 over 35. And I don't think that that reduces. And so there's our ordered pair. Okay. Okay, I'll try to go right over to my office and post up a review sheet. But first, today is Texas Tech's 98th birthday.
Wow.
And at 3 o'clock, like right now, giving out free cake at the sub. Come on through. I made the cake myself.
Were you talking to me?